Easier to expand. What else? You can configure it for what you need, right? Does that make sense? Configure it for what you need. Fixed PLCs, it's like when you go out and buy a tablet. You get what you buy, right? You understand that? You go out and buy like a desktop computer that's got a separate CPU, and you configure it the way you want. So that's what I have. My main computer at home is not I use laptops here. I got a tablet at home, but my main computer at home is a desktop. So what could I do? I got what I wanted, right? And I configured it the way I wanted and put the stuff in there that I wanted and not what some company figured I wanted. Another advantage of a modular PLC is they're easier to troubleshoot. We do a lot of what we call swapping stuff. So we get out there and something's going on with one of our modules, and then, okay, we come up and we think it might be the module. So what could we do? We could swap that module out without swapping out the PLC. Fixed PLCs, if something goes wrong, you got what you pay for. So it's a little easier to troubleshoot. But what we find out is that it's more expensive than a fixed PLC. It's just like Alabama Power. You notice when they run three-phase, you can buy three-phase transformers. They're in one unit. They're all bundled together. But if one of your transformers goes out, you have to replace the whole thing. What Alabama Power usually don't do that. Alabama Power usually runs 3 transformers, which originally is a lot more expensive, right? You understand that. But if one of their transformers goes out, they don't have to go out and replace a 3-phase transformer. They can go out and replace a single phase. So usually modular PLCs are more expensive. Your original investment is more expensive, but they're cheaper to maintain. Fixed PLCs are going to be a cheaper investment, right? So I go out and buy this, then I get what I pay. I get what I buy. I go out and buy a separate desktop with an individual CPU and a monitor and whatever. It's going to be more of an investment for me to start off with, right? You understand? But I get what I want, and it's easier to maintain. Are we okay? So we have places for both of them. So what a lot of them PLCs are doing now. Unfortunately, I've already snapped it on there, and I think I don't know how to get it off. What most of your PLCs are doing now, they're buy them as fixed, but they're basically modular. I call them hybrid. So what you do when you buy these guys is you get a fixed unit, and then what you can do is you can buy modules, but the modules are not in a rack. So when we talk, most of the time when we talk about a true modular PLC, it has a rack. We call this a rack right here. And then what you do is you buy a rack that's got so many slots on it. And then if you run out of slots, then you can buy another, just a rack, and then communicate with it using some of our communication methods. What's nice with these PLCs, these I call them hybrids, is these don't mount on a rack. These usually mount on something one of the standards is what we call a DIN rail. So this is a DIN rail right here. This is what they call a top hat DIN rail. It got the name from the company that specifies it, and it's a German company. I'm not going to say it because I don't know how to say it. But DIN is in their names. This is the DIN rail right here, and this is what we call a top hat DIN rail. And this is one of the first ones that came out. So basically, the PLC is set up so you just come in, and this will be mounted solid, and you just come in and slip it in. This is not set up right. So you come in and you slip it in, and then you snap it into place. And then once it's snapped into place, and so you mount the DIN rail. And how long can you make these DIN rails? Yeah, so this is one of the most popular ways to do this. I call this a a hybrid PLC because you buy it as a fixed, right? You understand, and then you buy modules that you want to do, and now you can customize it toward what you need at your plant. Okay, and then they've got all types of modules that come along with this. So this is the original PLC that I passed around. And of course, what I've done is stuck another module on there that we bought extra so we could hook this up to our Festo manufacturing line. We talked about syncing, sourcing. Everybody okay there? So when we talk about syncing and sourcing, this only deals with DC modules. We don't use the term syncing and sourcing for AC because AC technically has no polarity because the polarity is constantly reversing. Alabama Power reverses every 8.33 milliseconds. It changes polarity. And you don't know what milliseconds is. That'd be 0.0083 seconds. So for all practical purpose, and it reverses polarity. So from our point of view, we don't have a minus and a plus because this reversing happens so fast. DC never changes polarity. And so if you got DC input modules or DC output modules, this is where you're going to have to know if they're syncing or sourcing. And I think I showed you the little Allen Bradley 1100 that we have, where you can establish groups of inputs as syncing or sourcing. And what do we mean by that? So if I've got a syncing device, then I would have to hook it up to a sourcing input, right? Does that make sense? And if I've got a sourcing device, I would have to hook it up to a syncing input. Everybody understand that? Okay. So ours, if we look at this module right here, it says the input module says it's syncing. So that means it uses a negative common. And so that means my sensors have got to supply the positive, right? You understand, to complete the circuit. So if these syncing inputs means my input devices that I hook up to it have got to be sourcing devices. So they'll use a positive common. Does that make sense? Like this. So this is not syncing and sourcing, but if this was DC, they say AC on this one. I don't know if this figure is right or not, guys, but we'll just make up DC. So let's come over here and I'll say plus 24. And then this would go out, and this would be the common for all my inputs. So that means my inputs would be sourcing, so this module would have to be a what? Syncing module. You understand that? That makes sense? So over here on our outputs, so on the outputs, this is a sourcing output on the 504s. So that means they're common inside the PLC is a positive. So what would I have to send out through here? I would have to send a negative, good. And so we would say these devices would be syncing. And this only comes to play with DC. If you're dealing with DC. Okay? If you're dealing with AC, common is going to be whichever is going to be the neutral for the line. Looked at that, talked about the scan. So the scan goes, scans input, runs it through your program, updates output. We call this a scan cycle. And this is what the PLC is constantly doing. So your program is constantly looping whether you tell it to loop or not. Other programming language, we have to do that. So this PLC, these are what? Sourcing. So this input has to be what? This is thinking. So this guy would have to be good. We looked at the basic ladder diagram, right? We did one. So what Allen Bradley, and a lot of y'all that has played around with this. The way the addressing scheme is set up by Allen Bradley is that you start off, if it's an input module, you start up and say what? I, then you put a code. Now what they know now is it knows it's going to use that as an input. Then what the next thing you do is you specify a slot number. That makes sense? Then what you do is you specify words. So that would fall, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One of these are going to be where you establish the common. Well, no. So on a slotted PLC, this is slot 0.
I mean on the input.
Wait a minute.
You started at 1 for that first
Well, I was
group.
just trying to figure out how many groups of 16.
Oh, okay, sorry.
So I'm not going to start that one. Allen Bradley runs word numbers in groups of 16. If you got only one 16 module, then all you have to do is specify the slot number. But we can buy input modules for Allen Bradley that goes up to 2 words, which is 32 bits. Okay, does that make sense? So if I've got a 32-bit input module, then I would have to say, okay, what slot is it in? So this would say slot 1. And then I would specify the word number. Then I would specify the input that we're dealing with. Now these start with 0. Allen Bradley, they'll go from 0 to 15. Now if you don't have a 32-bit module, then you can leave off the word. You understand that? So ours are 32-bit modules. I'm sorry, ours are 16-bit modules. So the way we would address it on ours would be like this. All we'd have to do on this one, we'd have to come up and say, give me a pen color. Give me white. No, I'll do it. I need to do it in black, so I'll write down. So on ours, since ours is a 16-bit, ours is only a 16-bit module, then we would have to say N colon, and then we'd put a slot number, and then we would put a slash, and then we'd put a bit. Okay. Now if it was a 32-bit module, right, you understand, then it might go like this. It might go N colon, and then I'd say module number, and then I'd put a dot, and if I came up here and said 1/7, then it would be the second group of 16. That makes sense? Yes or no?
Why is it the second group?
Because 0 would be the first group. 1 would be the second group. Remember, in here, we start with 0. So this, on a modular PLC, this guy starts with slot 0. The CPU's in slot 0. The power supply does not occupy a slot. Okay, makes sense? So on this one, this is a 2 words, so that's common. So, looks like it has more than that to me. 1, 2, 3, 4, 5, 6, 7, 8. Oh, there, this, they didn't look at anything here, and they don't have anything up there. So this would be a 16-bit module, so they didn't have to put the watt in there. They didn't have to put the word address. That makes sense? So if you've only got a 16-bit module, you could address it like this. You could say input colon 1/0, and that's the number 1.
So when it has 32, it just like has 2 of those next to one another?
No, it's all on 1. So we're dealing with,
it has a 0 or a 1.
No, I'm talking about it's got a module like this, and it's got 16 down this side, and it's got 16 down that side on one module.
So what my question is then, you've got input colon 1 for the slot, then you put a dot, which lets you know that it's 32, right?
Right.
And then 0 for the first row, or 1 for the second row.
Right.
Okay, now I got it.
Yeah. If you don't have that, so ours are 16-bit modules, so we can address it N colon 1, and I need to make that 1 instead of a, I need to make sure y'all understand this. So this is an uppercase I, this would be a 1, and then that would be bit 3. And I think, which is this guy right here, right here. I think this don't have a number. So this one, that's what I need to do. So this one, and this one. No. What we do on binary, the bits have numbers and they go by the powers of 2s. So if I've got a 16-bit number, this bit right here would be 2 to the 0. So we start with 0. So this is 0, 1, 2, 3. So if you go by numbers, understand on this situation right here, it just worked out to be the third one. Understand? So if I say n, then I say colon, and then I say 1/8, then this would be 8 right there, and that would be the one. Yeah, but we start with 0. I'm sorry. In addressing, we start with 0. It is bit 3, but the first bit we call that what bit? No, what do we call that bit though? We call it bit 0. So the first bit is bit 0. Now this kind of gets confusing, especially on this PLC, because if you look at the first input switch, they got it labeled 1. So it goes 1, 2, 3, 4, 5, 6, 7.
I was looking at the input address up there.
Yeah, so this is slot, this is the word, and this is, when it says the terminal number, that is not counting, that's the number, that's the address that we assign to that number. Does that make sense? And we start counting from where? Start counting from 0. So this bit right here would be 0, this would be 1. So that's terminal, what they're calling terminal 0. Now I called it a bit number, and why? Yeah, I know, it's very confusing. What really gets confusing up here on this PLC is they number those switches 1, 2, 3, 4, 5, 6, 7. But switch 1 is addressed at 0. And somebody's going to make that mistake. They're going to be up here flipping switch 1, right? You understand? And their address is at 0 and nothing's going to happen. So that's not a terminal number. That's what we call a bit number. Everybody understand? Yes or no? Makes sense. So what happens is that when we come up here and this is a real neat application. But the problem is, if you've got that CD, you have to have that CD and a CD drive. So if you're doing this on a tablet or something that don't have a CD drive on, it's not going to do you good. The license for it is like, I think, $15. That comes in, it's in the lab book, I think. Isn't it?
No.
Oh, it's
The hardback book.
Yeah.
So first thing we do if we're going to create a program on Allen Bradley, so these are our instructions. So instructions are what we put in a program to tell what we want to do. And we have a list up here. What we're going to be dealing with in this semester is we're going to be dealing with these 4 guys right here. And then we're going to be dealing with timers and counters. But we're not there yet. So the first thing that we would have to do, can't get it to go. The first thing we have to do is, so by default on the Allen Bradley RS Logic software, it puts the end rung in there for you. You cannot put anything in the end rung. So the first thing we're going to do is insert a rung. Here's the rung instruction right here. So I'll just come up and highlight that. I hit this, and then it puts a new rung in there for me. You notice the end rung gets another number. And then what you do is you grab what you want and drive it down in here. The first thing that we needed to do, by the way, before I did this, so I messed up. The first thing you're going to have to do is you're going to say new, and then what's the first thing you're going to have to do? Select what CPU that you're compiling this for. Because every, that would be like you try to put an application off of Google Play into an iPhone. Well, it wouldn't work because it's been compiled for a different processor, right? You understand that? So you can get the games, the same games usually on both sites, but they're not compatible with each other. They just been compiled for a different processor. The one we got is we got the 1100, so we'll go down here to the MicroLogic. I'm sorry. See MicroLogic? Right here. We got the MicroLogic 1000s. So I'm going to select that. And now my compiler knows how to translate this up when we load it down to our computer. Then I'm going to come up here, I'm going to insert a run. Then I'm going to come in here and I'm going to put an input. Well, what I got to know is I got to know what this guy uses, right? So what we're going to do is I'm going to simulate the I/O. Oops. And this is what this PLC's got. Notice the first one is 0, 1, 2, 3. Well, that was the slot it's hooked up to the PLC. Okay. And I've got inputs on slot 1, and I've got inputs on slot 3. So those are the two slots I've got available. You got several symbols on this, which is really neat. So right now I've got a normally closed push button, but you can change it over to a limit switch, you can change it over to a switch or a push button. So what I'm going to do is I've got to tell the PLC where's this at. So I'm going to come and double click on that, and it's asking for a what? An address. So I'm going to say input, colon, and I'm going to choose that switch right there. So I'm going to say, what slot is it? 1/0. Okay? Okay? And I said enter. Now what's going to happen on the true Allen Bradley PLC is it's going to pop you up and want you to give a symbol name. And what's so neat, if you give symbol names, if you're going to use that same thing from now on, you don't have to know the address. All you got to know is the symbol. And then, of course, it makes it, and normally we give this thing symbol names according to what it does in here. If you don't do it, then you can come up here, you can actually add it. I'm going to put stop. So this is going to be, I'm going to make this stop, right? Does that make sense? Okay. Then what I'm going to do is I can do this several ways. I'm going to put a down drop right here. And then I'm going to come in and I'm going to put a normally open contact inside there.
This is all that disk.
Yeah, this is the simulator. Now you're going to run the real thing. It's called RS Logix. And right now we're having problems with this PLC, but I'll show you the whole real thing. This one's a little harder to configure because not only do you have to configure the CPU, you got to also configure the rack. Because when I have a fixed PLC, when I select a fixed PLC, it knows how many inputs it's got, it knows how many outputs it's got, it knows the addressing, it knows all that other kind of stuff. A modular PLC, that CPU has no idea what you got out there because you can configure that thing any way you want, right? You understand that? So what I'm going to have to do, I'm going to have to tell it. I'm going to have to tell it it's a 7-slot rack, and then I'm going to have to say, in this slot, I've got the what? An input port, and then I got to tell it what type of input I've got. And this is usually documented on the doors. So if you, any of these doors, you open them up and you look down at the bottom, and it'll give you the actual part number for that module. So I'm going to make this another switch. So I'm going to have to give it another address, right? I'm going to put N:1/1. And then when you hit it on the true RS Logix, it'll pop up asking you for a symbol name. If you just say, if you bypass that, then you can always come back and just right click on the icon for it and then do what? Edit symbols. And then it'll let you give it a name. Now, I don't know when this one, I know what it's going to be, but we'll see if it works on RS Logix. So we'll come up here, and this is a simulation, so everything is not exactly the same. So this is going to be an output, colon this. And, RS Logic, if you use lowercase letters, it'll take them as uppercase letters, so it's up to you. I'm not sure about Logic Pro. And then I'm going to say my output is in what slot? 2/0. Okay. And it did, it converted it over. We'll see if Logic Pro will let you do that. No. Oh, now on RS Logic, if you know the name, instead of putting the address, you can just give it. So the simulation is not exactly right. Now, when I chose that, it put the label in there for me. Now, the next thing that we're going to have to do is we're going to have to, once we get this, we're going to have to download this into the field. And this will be where you got this right here. And download the PLC. Okay. And what we did is we just put that program into the PLC. Now what's going to happen on Allen Bradley, everything you do is going to be over here. On this one, you got to go online. And then in program, you can't make major modifications to a program. You can make minor modifications. So most of your programming is going to be done offline. And then when you modify the program, then you'll be able to upload it. So you can't add any new elements. You might be able to change like a symbol name or something like that. So it's very, very minor changes that you can make. And then we can switch this into run. Now it automatically came up and showed that one right there is made because it's a normal code contact, right?
So when you download it to the PLC, it says it's going to be online.
Yeah. The 504 has a mode selector switch on it, which is key protected, and that's this guy right here. And you got 3 options. You got program, you got remote, and you got run. If you put it on remote, then you can switch it between online and offline and run. You can switch it from software. If you put it on program, it'll let you download the program, but to run it, you'll have to do what? You'll have to change the switch to run. Now, why they do that, if they don't want somebody screwing around with the program, is they switch that sucker to run and take that key out. And then that means even if you've got a computer and you hook it up to that thing and you've got the application, you cannot, if you hook to it, you won't be able to do what? Change it. Just about all your fixed PLCs do not have, it's by software. So you switch between run and program and on and offline by clicking on this little window on that little scroll bar on the right hand side, a little scroll window. You can understand because the more stuff they put out there, the more complex it's going to be, right? And some of your hybrid PLCs have gone back to that switch. We got the Micrologic 2300s over there, and they actually got the switch on there again. And that's just an extra safety procedure unless you lose the key. So I guess you can get another one made. So we just leave the key in here all the time. And if you put it on remote, you don't have to constantly do switch it back and forth. And so this is simulation. We'll come up here and do it in real life in a second. And we call this a memory circuit because it automatically seals itself in. See how that works? So as soon as I energized this coil, it came over here and did what? Close that contact, and now it can make away. And notice my output it comes on. In fact, right now we've got lights out there, but we could hook up a relay to that, or a small motor, or a small something, right? That the PLC might have the ability to run. Are we
Do it
okay?
again, start it, please.
What's that?
Turn it off.
Okay, so to turn it off, what we'd have to do is hit this button right here. Right? And then that opens the circuit. the relay dropped out. We call this a memory circuit. We call this a sealing circuit. Some people call it 3-wire controls.
And then when you activate it, you activate the start, right? And then do that again.
So this is a normally open. So when I hit this button right here, this closed. This completes the path to this guy right here. So this guy becomes true. As soon as it becomes true, it closes that contact right there. So now I got a secondary path. So now I can come through here. So I'm gonna come up here and just touch this button. This is a momentary contact button. So I just do this. As soon as I let it go, it seals itself in. So now it's on power source. By the way, for some reason in Germany, over here in the USA, we usually put the start button to the left of the sealing circuit. In Germany, they put the start button to the right of the sealing circuit. But it works exactly the same. It's in series. So if I open that up, it's going to kill power to this simulated relay coil, and it'll drop it out. So that's something that we learned over there. So when we,
MCR is modular.
what's that?
MCR.
It's just a number I came up with. I call it a master control relay. Because what I could do is we could come up here now, and I'm going to take this guy offline so I can program it. So what I'm going to do is I'm going to click right here, and I'm going to insert another rung. Well, down here, I'm going to come up here, and I'm going to put a contact, but I'm going to give it the name of that relay over there. Output, colon, 2/0. And then I'm going to use another output. I'm going to specify one of our outputs. Okay, and we'll say this is output 4 output colon 4/0, which would be this guy right here. And then I can give it a name. So here we'll just call it a light. The names are what you come up with. Now normally companies do this. They assign these things names. So instead of me saying output here, output there, they say, well, that's the start, that's the stop, that's your master control relay. And like I said, in RS Logix, once you assign a name, if you type that name up there in that bar instead of an address, it will automatically assign the address for you, which makes it real easy. So now you're not worrying about outputs. You say, well, I want to use my start button. Well, you don't, now from now on, you don't have to know. And Siemens call them tags. So what you do, here Allen Bradley calls them symbols. Siemens call them tags. So what you do is you assign a tag to everything. And it's the same thing. It's just a little word or something that makes it from now on, you can do what? You can deal with that name instead of trying to remember all these addresses. I'll let you, huh?
I was just wondering why you labeled that one and output that could be because it's connected to the 020 where that normally open is on your first.
Yeah, well, this is module 4 right here. It's another output port.
Your input, well, what I would think was a normally open input on your rung 1, not rung 0, rung 1, that first one, the motor control relay. I guess it's connected to your output up here, but you labeled it 0 or O colon 2.
What? This?
No, is there another on your next rung, that first input?
No, what we're doing is this is not an input. This is a contact being controlled by that relay.
I think that's the only thing I just can't get.
So what we can do is that, so do you understand that this is not an input?
Yes.
This is a contact being controlled by that relay. So when I energize this is going to close this contact. This is a contact being controlled by that relay. So when I energize this is going to close. This is not an input. This is a contact being controlled by a relay.
So when they close, then that light.
Yeah, so watch this. So now when I come up here, what I have to do now, I made modifications. What I got to do now? Yeah, I got to come up here and download it. Normally you have a download and go online. It'll automatically do that for you. No, it didn't. I think the Allen Bradley does that. Go online, switch this to run. Okay. So notice now when I come over here and press this button, Okay, so this guy came in, this sealed it in, because that symbol, I didn't assign that symbol to a input. I assigned that symbol to a contact being controlled by a relay. So this contact right here closed. This contact right here closed. What made this one close? Not an input. This relay right here closed this one, and now this light came on over here. So you can, and what's nice about when you buy a relay, you buy it according to the number of contacts on it. That's one of the things you specify. How many contacts what I can have? Well, we can have up to 256 on Allen Bradley. So I could assign up to 256 software contacts without, I mean, what would happen if I was out at, what would happen if I was out at Mercedes and I had to go over there and push a button to make everything work? So we have a master control relay. We hit one and we hit start, and then that fires up everything and it just takes off. Now normally we have a master control relay, right? That we can do what? That we can hit one button and everything stops. And that would happen. So normally what I would do now, if I wanted it to work like that, I would put one of these contacts in every what? Every run. At the start of every run or somewhere in the run. And we'll talk about later about the intro. We have the ability to simulate this. So let's say I don't want to sacrifice one of my true outputs for something that don't need an output. So this guy right here don't need an output. All we're doing with it is turning on a light. So what I'm going to do is I'm going to go back offline, and I'm going to change this address to B:0. B3 started. So this is my only true output right here. It don't change the symbol. So Logic Pro is not exactly up to par. So okay. By the way, anytime you create a rung, and I'm going to show you all the actual thing, so you get an arrow here until you get everything straight on the rung. Logic Pro doesn't do that. Okay. So I'm going to come up here, and of course I lost my symbol. So let's go online. So what we've done here is this guy right here don't exist physically. It's totally software. It's inside the PLC. Because you're thinking, okay, I've got to use, for all my relays, I've got to assign it to an output. You only need to assign it to an output if you need to drive something outside, right? Does that make sense? We call this a soft contact or relay. Watch, it works exactly the same way. So now here, the only output that's working is the one that I want to physically do something. This right here it's inside the PLC.
How did you know that?
Because I knew it. We have two what they call bit registers inside the Allen Bradley. We have the V3 register. You can use it for all kinds of things. And we have some of them have what they call a V10 register. I don't remember if the 1000s have got the V10 in it or not. I know the 504 does. So that's 512 things that you can use without actually making it physical, without generating physical output. And so this is the way I would do this circuit right here. This couldn't be an E-stop circuit because E-stop's got to be hardware, right? You understand? But I could definitely do that, simulate that contact with software. So the V3 register is really neat. We got some really neat registers too that we could do. Timing registers, it's really neat that things that Allen Bradley does for you. I hadn't been able to find it in the Siemens, but I'm pretty sure I'm new to the Siemens. So how to address that other module on that guy right there, I don't know. I got to figure it out.
So the program you're running, you
Yeah,
go
wow.
online, and you got to put it on run, the program.
Well, yes and no. This is a simulation. What you're gonna do on RS Logic is when you download it, right off the bat, it's gonna say, do you wanna go, if you got it on remote, when you download it, it's gonna ask you, do you wanna go to run? When you click on it, it'll take you directly to run, which saves you some steps. If you're using the switch up there and you don't have it on remote, then you're gonna have to switch it from program to what? To run. You can understand the advantage of that. So if you got it in run, you can't upload or download the program that's in there. So you can upload and it's backwards, but you can upload the program from the PLC into your program. So even if you don't have the program, if somebody had done that and you got the applications, that would probably be one of the first things you would do. You'd go out there and do what? Upload those dang things and get copies of them. Now the only problem when you upload them, when you download them into the PLC, the symbols are not downloaded. The symbols are all solved. The addresses will be the same, but there won't be any symbols. So if you upload one down into your computer, you're not going to get any symbols. So I think Siemens actually puts the tags in there as part of the program. So this would be this is RS Logix. So this is the actual software. Let's see what else we got in here first. Make sure we get through this. We okay there? So this would be a 32-bit module. So this is really good. This is a really good picture. So this is a 32-bit input module, right? You understand? So now if I've got a 32-bit input module, since Allen Bradley goes in 16, then this would be word 0 and this would be word 1. But if all you got is a 16-bit input module or less, then you don't have to specify the word number. You just specify the slot number. That makes sense? That makes sense? So we don't have to specify it here. Input, output, syncing, sourcing, we already looked at that, right? This shows you how we would hook that up. So this is the way it's done right here. So we actually got two circuits. And this would be the input mod. This would be the actual input. But what happens is the circuitry inside there with it, which they don't show, it's actually hooked up to the other line right here. And they don't show this. So all your outputs are hooked up to a common over here too. That makes sense? Because it's all computers, this is the big difference. So that means if I come over here and then this right here is a minus, then these over here has to be a what? Plus. Right? You understand that? That makes sense? So we would say the inputs would be syncing, and I'm sorry, the PLC inputs would be syncing and the input devices would be what? Sourcing. Now, if this is AC, you'll establish a common on AC, and there's no such thing as syncing and sourcing. It only comes into play. Now, sensors, what did I tell you about the sensors? They're going to be called what? NPN or what? PNP. NPNs are syncing sensors, PNPs are sourcing. Sourcing, syncing. So I think we've explained that pretty well, right? Sourcing, syncing, and then this is where we're at now. Okay. When we open up a program, what I'm going to do is I'm going to escape from this, and then I'm going to have to actually open up the RS Logic software. First of all, we have different methods that we communicate with the PLC. We have different type, what we call them interfaces. Allen Bradley uses what they call the device. They call it DF1. It has really no acronym. They have what they call the data highway, which is a DH method. They have Ether IP, which is basically Ethernet, and they have DeviceNet. Siemens uses uses Profibus, and they use Ethernet, what they call Profinet. So one of the first things that you're going to have to do is now all our PLCs should be set up already. But if you're hooking up a new PLC to that, first thing you're going to have to do is tell this thing, how do I need to communicate with the PLC? So Alan Bradley has a application called RS Links. And I don't see it, so I'm going to bring it up. So I've got this PLC right here, and I've got mine set up right now for Ethernet. So I'm going to have to reset up the way it communicates with this PLC. So Rockwell Software, and we're going to use RS Links. And then we'll come up here and just say communication. And then I should have checked this out before. Configure driver. So we know basically what a driver is now, right? What's a driver? It's a piece of software that controls hardware, right? And it's already running, so I'm going to configure it, and then I'm going to just tell it to auto configure and look for it, and it's there. So what we do on DFI, we got D8 data highway. We got two ways we can do it. We can do it in what they call a bus architecture, which means we run a big old long coaxial cable. Y'all know what coaxial cable is? It's cable that they run in your cable TV. But the cable that we use for the data highway is a two conductor shielded cable. So you can't just go out and buy a TV cable and use it. This is a special cable you buy. And it's got some screws on the front. I'll have to show you that. The other method you can do is through the old RS-232 interface, which was originally put out by the Electronic Industries Association, but they disbanded EIA, and it's been taken over by the Telecommunication Industries Association. And what that does is it specifies this guy right here. And this is what we call a D-type connector because it's in the shape of a D, right? And it's a 9-pin connector. And what's data and all that kind of stuff is identified by the RS-232 connector. Okay. This was the original connector they used for the mice on the IBM PCs before they went to the round connector. So what eventually happened is instead of using this guy, they switched over to this guy. So now your older IBMs, before they dropped it off, this was the RS-232 connector. So what you're going to find out is that this guy's got a DB9 on front of it, okay? But if we looked at the 1100s, it's going to have this guy on there. Now the problem is our computer no longer has these ports on there. But it's no big deal because we buy these things they call dongles. Where's my dongle at? Right here. And so on this side, this is USB. This is an A connector. A B connector, standard B connector. And then this converts it over to RS-232 for you. Okay. So if you're going to hook up using this method, now the most popular way to go now is what? Ethernet. So Ethernet. But both of our PLCs, the 1000s and the 504s, still use this. So you have to know the COM port you're on. Then you can auto configure it. Now we're ready. So now I'm configured and it's up and running. You can run multiple protocols on here at the same time, multiple drivers. So I still have my Ethernet driver. So hopefully we'll be able to connect to this PLC. So I'm going to come up and run the RS Logic software. Dang it. Okay. And we're going to come up here and set up a new program, right? And what's the first thing I got to do? Got to select the processor. By the way, this is a 504, but Allen Bradley don't go by 504, they go by model number. So what you do is somewhere on that PLC is the model number. On the slotted PLC, when you open the door, down at the very bottom, it gives you the model number. So this is a 1747 541. So I'm gonna go down here and select 747 541. And there it is right there. Okay. And then it brings this up to them. But the problem is it's a modular PLC. And that's where all this information is over here. So if I go over there, this tells me the processor I have selected. Okay. You can give the processor a name, by the way. So I said I could call this processor Ridge. But I'm gonna configure the I/O. And what's the first thing we need to do? Well, right now we got to do, this is a rack PLC. They know that, but by default it comes up and says I have a 4-slot rack and I have a 7-slot rack. So what's the first thing I need to do? I'm gonna come up here on this one and choose a 7-slot rack, rack, not this one. This is multiple racks, so this guy would support up to 3 different racks. And you got a cable on the side that you could just jump down, and this would give you the ability to expand it. Now what I have to do, so it shows me that slot 0 is occupied by the CPU itself. So now I'm going to say what's in slot 1. The input. Now this is going to show everything. So what I'm going to do is I'm just going to go to inputs, and then on your input module you'll see the same thing. This is a B16, this guy right here. Now, so it's a syncing module, right? 16 inputs. Where would that information be at? It's going to be on the little flat of the door. Look down at the bottom of the door. I know it's time for a break, guys. Then I would come down and I'm going to select nothing but outputs. Now, if you get on one of the 1100s, you don't have to, on the 1000s, you don't have to do this because it's a fixed PLC. If you get one of the 504s, you're going to have to do this every time you make a new program. But it don't take long after a while. This is a B16, and then I'm through. Now I'm ready to start programming this. So my PLC knows all the instructions I want. It's all up here. Oh no, this is supposed to be activated. I'm gonna have to see what's going on. I'm gonna put this in here. I'm gonna pop that in. Notice it on this one right off the bat. It put all these E's over on the left-hand side. That means I got an error on that run. Why? Because I don't have anything in it, right? So right now I got a short circuit, which is definitely an error. Then I'll come up here and I'll do the same thing. I'm gonna assign an input. But now I'm gonna have to, what's the slot number for that? N : slot 1 0. Okay. And notice on here it comes up asking me for a watt, a symbol. But you can put a comment up there. Oh, it's not stop.
You don't put the oh well. I was just wondering if you didn't put the address in that blank spot.
No, you've already got the address. Still got a error because I don't have an output. I'm gonna come up. Well, we'll have an error too. I'm gonna come up here and assign an output, and my output is what? Module 2. Huh? No, that's a simulation. This is the real guy. So what I'm doing, that's the button right there. That's the guy right there. Okay, understand that. And then when I enter this, it's going to ask me for a symbol. You can say okay. If you do that, you can come back later on by right-clicking it and giving it a symbol number. Yeah, Siemens call theirs tags. I hit the capital lock key. Mute. And we'll see if this works. So I'm gonna come up now. The run would be clean, and this is what this is for right here. You can check it, and it tells me that that guy it's no syntax error. Syntax is the correct way of writing instruction. It don't mean there's nothing wrong with it. It just means there still might be something wrong with it. I might have assigned it a module that's not available, right? You understand that? And when I upload it, it's going to say, hey, I don't have this module. So it don't mean that don't mean this will download, excuse me. So let's go ahead and do the other one. Y'all go ahead and take a break. I'm going to do the same thing. Oh, well. That was good. So I should have let that fall. I'm gonna delete that and let y'all show you can actually do with the regular. Okay, what's your last name? Irvin. Okay. I can do that right now since we're right. That guy's probably gonna do this.
I noticed, I didn't know, but I was like, I'm.
So we got this power, we got that push set right there. And it comes to that normally closed push button, and what's it waiting on? I press that one, all I have to do is press it. It's a momentary contact. As soon as I do that, that relay, that contact right there closes. Now I have push right there, and what can I do with my start button? I can release it. Now the problem with PLCs is that we have a switch that we hook up to a port. And as soon as I go into digital, I'm not talking about closed and open. I'm talking about true and false. What is true and what is false? Okay, y'all understand that? So when I come here and I actually look at these I/O tables right here, so you can look and see what's going on digitally on your I/O. When I close that switch right there, what does that bit in memory do? So this is a bit in memory. So that's a byte that's a word in memory. There's the bit. I'm going to close that switch. So here I'm going to come up here and I'm going to close that switch. And what does it go to? It goes to 1. Is that true or false? Is it true or false?
You got a definition for those?
It could be either a true or it could be a false. It's just like I could put a glass up here and I could say if the glass is empty, it's true. If it's full, it's false. Or I could just as well say if the glass is full, it's true. So what we do is we say, okay, what does this mean? It means that switch is closed. Well, if I say examine if closed, if I use an examine if closed, then a 1 in this table is true. If I put an examine if false, if I put examine if open, then a 1 in this table is false. So you understand? So right now I'm using examine if open. Right? You understand? So this is a 1, but I'm using an examine is open. So that sucker says, okay, that's false, and nothing works because I'm using an examine if open contact. Well, but that instruction is an examine if open instruction.
Communication is what is true, where it sees the communication.
What it interprets this right here as. So if I'm using an examine if open, then it's going to look for this to be a 0. So watch what happens when this goes to a 0. So I'm going to make it go to a 0. And that sucker up there becomes true. So if I use an examine if open, then it's looking for an open contact coming in, right? If I use an examine if closed, it's looking for a 1 means a close. It means it's closed, right? You understand that? Ain't that neat? So right now, this is what it's reading from that port, and it went true because that is an examine if open. So that means what I would have to do to make this thing work is I would have to get a 0 in this data table right here. which means I'd have to use a normally open push button. Because it's open right now, right? You understand? Now, what's the problem with using a normally open push button as a stop button? If the wire breaks, it's going to be open anyway, and you cannot stop your motor. And that's not good, right? You understand? And this is one of the concepts that gives people problems with examine if open and examine if closed. Because what we're getting back, if they in this data table right here, if I get a 1 back, it means that switch is closed. If I get a 0 back, it means that switch is open. What you're doing with your instruction is you're identifying what is true and what is false. So right now, and I like to demonstrate this with that guy over there. I might do that and pull that wire out on the stop button, and I'm gonna go over and just hit it 100 times, and the motor's not gonna stop because I use an examine if closed. Now, why people get in problems with this is they come in from motor controls, and in motor controls, that has got to be a normally closed push button when you wire it electrically. But when you're in a PLC, this is all logic.
Go back to your drawing for just a second. The last slide where you were just drawing.
This is not a PLC program. This is a motor control circuit.
I have a question that I wondered about, but can I come up there for a second? Because what you've got is, let me show you. What you're saying is, that's it's also that's examine if open. Correct?
No, that is a normally closed push
That's what I
button.
meant. Okay.
If I was going to program it into a PLC, I would use an examine if closed.
That's this on the face.
So that's this one?
Huh?
See, has it on the face. That's what that is. That's what right there.
But this is what it looks like when you're programming it. Is that correct?
No.
No.
It's the other one.
Yeah. Because that is an examine if open. We want it to be true when it's what? When it's closed. So in PLCs, this guy right here, examine if closed, that means it's true when it's closed. This right here in PLCs, this is an examine if open, that means it's true when it's open.
So it's kind of like our.
Yeah.
So logically, I would think the word examine means if it's,
Means it's true.
you need the.
Examine it, but they call it examine if open, examine if closed. So if you looked at the
What
name,
you're supposed to be doing is true. That's what you're looking for, and that's true. It's not what you're looking for.
but see, that's the problem in computers, is computers, we're not dealing with physical things. We are dealing with it, but we're dealing with programs. And they had to specify, okay, what are we looking for here? So this is, in real life, I would use a normally closed push button. My stop button would be normally closed push button, and my start button would be normally open. Well, the problem is that if I was going to come down here and I was going to use a contact, and this is what gets people confused, is I would come down here, and if I came over here and did this, and I came over here and did this, then that light would be on if MCR. And that's a normally closed contact. Well, see, in PLCs, we don't say normally closed contacts and normally open contacts. We say examine if open, examine if closed. You understand? And if I was going to program that into a PLC, then I would come up here, I would use this, I would use this. I'm not going to assign addresses. I would use this, I would use this, I would come up here and use this. And down here, I would come up here and do that. And that's what gets people confused. Because down here, that is a simulated contact, and it's going to be true when that thing says, okay, turn that thing off, right? You understand? So this is what gets people confused. So if you're doing it by a relay, if you want to do an examine if open, and that's what's going to happen. It's going to open that bit, and it's going to do that. So this is a simulated contact that I would assign to that guy right there, right? Does that make sense? But the problem is, if I use the stop button, I got to use the what? Examine if closed, which is, and this is one of the hardest concepts for people to understand. They'll get in there and you come out of motor controls and they'll say, well, that's the problem. You're using a normally open contact. You're using a normally open contact for that right there. It's supposed to be normally closed. How many times have I heard that? Good gracious. That even happened when we were over in Germany, where somebody came out of controls and had any experience with PLCs. So right now, this is what I'm reading. This is what my computer's reading back from an input. It's reading what? A 0, which means the switch is open. But it's true, because this is an examine if what? No, this is an examine if open. So you can do that. I think you can do that. If we take it back to, instead of dragging it down, let me look here. Let's go offline. And then I think we can change, yeah, so.
The pulse has nothing to do with what the switch is doing, it's reading what the switch is
Right.
doing.
So in that table, if that switch is closed, you get a 1 in that table. If that switch is open, you get a 0 in that table. What you're doing is telling the PLC to say what is a 1 and a 0 equal to.
Whenever you're off and on switches on the back of the computer.
Yeah, but that's what you're defining. You're defining they put a 0 and a 1.
That's what those marks mean.
The little circle with the dash in it, that's a 0 and a 1.
I never knew that.
Well, you do now. So, by the way, we can change this around, I think. So let's see, what do we got? Edit symbol. No, we don't want to edit the symbol. I thought we could change it right here. So what you're going to have to do on this guy, and this is what I want you to do once we get into these master control relays, is what you do on this one is your stop button would just be up all the time, right? And that simulates a normally closed contact. You can't do to do this on the 11,000s. The only thing you got on the 1,000, the only thing you got. The only push buttons you got are these guys right here, and guess what? They're all normally open. So what you'll have to do is assign your stop button to one of these selectors. You'll close it, and then you'll simulate a normal closed push button. Right? But you won't have to do that until we get later on in the program. When you take advanced PLCs, every program you write is going to have a master controller. Every one of them. Because that's usually what you see out in the industry, right? It's always nice to have one button. You can do what? You can hit it and it shuts everything down. Not an e-stop. An e-stop is special. So on our robots, we have a hold button or a 0 button or a 1 button. And then we got an e-stop button. And we got a dead man switch that's in the e-stop button. And you got a robot that's moving around 500 pounds, and you get the e-stop, and that sucker stops. Well, what's going to probably happen to the load? Yeah. So we have these controlled shutdowns that we have on our robots. So normally, if you're jogging that robot, you don't. Yeah, it'll slow down like you do on your car. Can you imagine? It's kind of like you're going at 60 miles an hour and you hit a tree. What happens? You happen. Not good, right? So normally you use the control stop. Even when you slam on your brakes, you don't stop, right? You still do what? You still decelerate. But most of us, when we hit our brakes, we do a controlled stop. We just slow down gradually, right, before we hold it back. So we don't like to do that. So if we use this type of thing, we could actually send the thing to a controlled stop. I mean, we could actually decelerate the motors instead of stopping them and doing stuff like that. So let's change. I thought we could change it right here, guys. Delete, change instruction. So here it is. So right now it's an examine open, right? You understand? And I want to change it to a what? Now it should run. So this is the actual physical PLC, and this is basically it. Now, all we're going to do is just do more complex programs. But the process of uploading, every time you create a program, what's the first thing you're gonna have to do? You're gonna have to set up the CPU, right? If you're doing this guy, what are you gonna have to do? Yeah, you're gonna have to assign the rack, right? And how do you do that? So once you assign a processor, then you go to IO configuration, and then you assign the rack. And we're using a 7-module rack, right? And then you assign the input. Well, it doesn't make any difference. The inputs or the outputs. But it'll have a number over here. It'll have a slot number over here where you come up and you select what slot it's in. Of course, the CPU is slot 0, right? So this would be slot 1. This would be slot 2. Modular PLCs, if you don't put a module on the side, on these hybrid PLCs, if you don't put a module on the side, your inputs are going to be module 0 and your outputs are going to be module 0. Because they're all fixed. They're not addressed by a slot, right? Are you okay? That makes sense? Huh?
I think
More or less.
most on switches are open, most off switches.
If you're going to use it as an off switch, a true mechanical switch. Now inside your program, everything is soft. So if you need a normally closed soft contact, you're going to use a lock. So let's go ahead and do that. So
You need true off.
yeah. So I'm going to come up here, I'm going to insert another rung, and then I'm going to come up here and I'm going to put another contact right here. And then I'm going to come up here and I'm sorry. And what I'm going to do with this guy is I'm going to assign it a contact off of this relay right here. Which one you want to do? We'll assign it to so let's do output 0/0. Okay. And notice it automatically gave me that. Of course, I could have typed that in, by the way. And we'll assign this another output. So output output 0/. And we might do like, it could be motor. I could assign it to motor. We're going to pass over. Okay. Yeah. I'm going to check it for errors. Oops, got an error somewhere. What's the matter?
You do. The NCR, does that matter when you label your last output? You put NCR, so it doesn't match maybe?
No, it does match because I'm assigning to this relay right here.
Okay.
Okay, let's go ahead and create one. It's going to pop an E up there because you got short circuits. And then that's what you do is you hit that little check button right up there. Of course, I can't do it now because we're online. Okay, now I've changed. No, it didn't change. Okay, so let me go offline, right? Because I changed it when I was online. Yeah. And I'm going to come back here and I'm going to change this backwards. So I change instruction type. So I'm going to change this to examine if closed. And it gave me an error, right? And I'm going to come up here and check it. And now the change should be made. So that's an examine if closed. Okay, so I'm going to upload it or download it. Excuse me. And it asks me, do I want to switch to the run mode? Switch back to run. Now what I'm going to do now is I'm going to change my contact over to a normally closed system, which is what I want. And I'm using the examining close. And what does it go automatically off that? Should have went true. So it went true. So now if I run it, I'm still using this switch right here to run it. I can still stop it. I'm still using the switch. I didn't wire it up. I can wire it up. Doesn't have to stop. And so now if we got something happen out there and we got a broke wire, it stops. And then I can wire back up. I can wire the circuit. So I've already got a common over here, so I'm just going to jump my common over to the next switch. And then I'm going to take that and put this in here. Make sure this switch is in the neutral position. And we're using input number 1. Which is right there. This is on working contact. This is not closed. I'm using the examiner. Closed. So it's closed if it's true. So that's why I can go on my pressing the screen now, this is what it would be. Now if something happens and I break that wire, then what's going to happen? It's going to stop. Now what you got to understand is that this is a true mechanical device that's hooked up to an input. And it's a push button. When you get into sensors and stuff like that, that's what you got to realize. What does that sensor give you back when it's true, right? You understand? If it gives you back a voltage, then you want to use it to examine it closed, right? You understand? When it's true. If it gives you back a minus, then you want to use an examine it open from that sensor because that's what it's going to give you back, right? So you need to know what that sensor gives you back when it's true. When whatever detects is true. If it gives you back a voltage, that means you're going to use an examinative close. If it gives you back your common, you're going to use an examinative open, right? You understand that? Now, once we get this inside a program, so this is normally closed, but this is a soft contact. And it shows this is true because it's not being controlled by a switch that's coming in on the input. This guy is being controlled by that instruction up there. There is no real relay. There is no real relay. Y'all understand that? That up there, that thing represents an output port. When it goes true, it just happens that it switches an output port true. And then what I hook up to that output port is up to me. So that's an output instruction right there. Is it going to a motor? No, it's going, I can have it turn on a light, right? I can have it energize a solenoid. I can have it do whatever I want to. But we draw it as a relay. So that is an output instruction. And it would still be an output instruction, but it wouldn't be designated to an output port. So what those B3s, those are logical relays. So it would be called a internal. So we call that an internal relay. We call these an output, so we say that's an internal relay instruction. So those are soft, and we use a lot of those because we get into PLCs, and a lot of people think you got to assign an output port to every instruction. Well, the only reason you need to assign a true output port is if you need to send something to the outside world. As long as it's inside, and this is what's really, really, really dropped down on the number of relays that's required to do a job, because now the only relays you're going to have outside are the ones that's running motors. All the other thing is what? And you do these things. So we got a counter. A counter is a counter, but it's logical, right? You understand? I can come over and I can switch that switch so many times, it'll count. And then we say, okay, what do you want to do when the count is up? We can assign it to an output, or we can assign it to an internal relay. It's up to you. So we have internal relays and we have output. So if I start off with out, then I'm assigning it to one of these dang output pins on this PLC. If I use a B, a B3, or a B10, then that's going to be an internal contact or internal relay. So if I've got something that don't need to generate output, it's just in there to make decisions, right? You understand? then we would assign it to an input, and we don't sacrifice one of our outputs. So I've seen people use outputs and don't ever hook anything up to them because that's what they thought, that's what they learned, right? They think they've got to generate an output, but you don't. So yeah, so this is true because that right there is false. But this is an internal relation. This is an internal concept, right? You understand? This is software. This is program. If I put an I, I'm actually got so this you do it just like you normally would in a motor control electrical control. It's just that where we run into problems up here is when we actually hook a device up to an input port, what's true and what's false. Well, if it gets a voltage back, it's going to put a 1 in that table. If it gets no voltage back, it's going to put a 0 in that table, and it's up to you to decide what that 1 and what that 0 means. So guys, this is it. Now we can come up here and we can throw some fancy programs together, just learning what we're doing. So we're going to learn about OR logic. We're going to learn about it. We call that right there OR. So OR means either or. One of those things could energize that core. Of course, we're using that as a memory circuit. So normally closed. So now, but if I look at the actual input, here's my input. Okay. So what we're using, we're saying right there, we're saying if this thing, this is examine if closed. So now it's interpreting that 1 as being true, right? Understand? If I come over here and push this down, then it goes to 0. So that's what you're doing. You're saying, okay, what is that 1? Does it mean that thing is closed, or does it mean it's open? That's one of the two hardest concepts to understand, is that examine if open and examining closed and syncing and sourcing. That's the two one of the hardest concepts to understand. In one class, I'll show you how we would do this with the Siemens PLCs. Siemens don't call theirs rungs. Allen Bradley calls theirs rungs because this is what we call them in electrical control. Siemens calls them networks. So what you do is you set up for every rung, you establish what they call a new network. And then you would do the same thing. You have on that, on the Siemens, you don't have to go through that whole thing up there finding your instruction. All your instructions over here on the right hand side of the menu. We do have all the instructions up here, if I can remember how to get to it. Yeah, this is the instruction palette right here. So instead of going through all these menus, let's go offline. If you bring up your instruction palette, then you can grab anything you want to over here and slide it in, I think. Oh, let's see. We have to.
Introduce Siemens stuff in the
PLC2, we'll go over to the lab and we'll put a basic program in. It's basically this program here, just to let you see the differences. We don't have enough time to teach you. It does everything that you do. It's got counters, it's got timers, it's got compared instructions, it's got all these high-level instructions. But all we have time in that is just to let you put a simple program in. When we get into, and I think what I'm going to do is, we got a bunch of these. I think in PLC2, we're going to let you wire up on one of these panels. Actually wire the PLC up. So this is actually wiring for the PLC, and these runs through slots to this front panel. And then once you get the front panel lined up, then you can insert anything you want to in there to make it work. So yeah, so here if I wanted to use an add instruction, I could just come in. So instead of me trying to go through here and find the different instructions through all these different palettes, if you bring that up, you can just leave that up. You can drag anything you want to. And how do you get to that? It's this little guy right here. That'll bring up your what they call your instruction palette. But you got to know mnemonics. What all these mean. After a while, some are obvious and then get into a jump certain things. And this is the kind of stuff we're learning in advanced PLC. Jump instructions, jump subroutine instructions, how we can feel, how we can do different things. We'll deal, in this class, we'll deal with these basic instructions right here. I don't know if we use the latching relay or not. I think we have what we call a latching relay. It's a relay that once you latch it, the only way you can undo it is if you unlatch it. We use this a lot on like on electromagnets that's on cranes and stuff like that. Because if power fails to your main crane thing, you don't want that sucker to do what? Drop. If you had a regular relay out there, it would unlatch, right?
We have a relay for on, a relay for off.
We have an unlatch and latch.
Oh, yeah.
Yeah, so we actually got a latch. We got a true latch. So it's actually got two coils on it. One you can't see. So one of the coils is right here. The other coil is right here. So what you'd have to do is you'd have to energize it and it's latched right now. So I'd have to get to this plunger to unlatch it. So right now it's latched. And to unlatch it, I'd have to come in and put both on this coil right here. And that would cause it to unlatch. So it means if power fell right here, it wouldn't do what? It wouldn't drop your load or whatever. So we can simulate that in real life. The only thing I remember using on it at US Steel was on the magnet control circuit. What's that? We put two different coils. I think I don't remember if we have a lab in that or not. I know we do latching and unlatching relays, but I can't remember if it's in advanced PLCs or this class right here. So let's see if we've done everything in this chapter right here, guys. Thinking, sorting. So this is some of the memory that you can actually look at right here. So over here it's called data files. So if you want to monitor your outputs, you just come up here and do what? Gotta go online. So this would be your actual outputs, right? That makes sense? This is where you'd monitor your inputs. So right now, if I look at my outputs, it says that this one right here is true, right? And there it is right there, it's true, right? See that? Makes sense? Here's our inputs. And it's telling us that this guy right here is true. So these are actually data files. This is our status register. The S4 register is a really neat register. It's actually constantly running. Can you see it's just counting? So what we do, if we know the speed of it, we can use the different bits, time delays and stuff like that is built into the PLC. But it shows us our errors. So if we got any errors, luckily it says no errors. It shows us our processor, what's going on there. This is your B3 register. We're not using that in this lab. These are where your timers will be at. This is where you can monitor your counter memory, your control register, which we don't get to in this class. This is where you can deal with your integers. You know what an integer is? Now, what's an integer? It has a whole number. So an integer is a whole number. It doesn't have a fraction. If we're going to deal with fractions, we'll have to switch over to floating point numbers. But here's all your memory files right here. Here's ladder 2. So we call, the name of this file is called ladder 2. So if I get off somewhere and can't get it, I can double click on that. And so this is file number 2. Later on in advanced PLCs, we'll show you how to add different ladders to this application called subroutines. So if you add another one, you'll have a file 3, and then over here you get a ladder 3. The S registers you see there, those have blood in them. This is actually the operating system. That's what you can change. Yeah, you can't see it. Notice it's got the circle with it. So these are the different. These are actual different registers or memory locations that's assigned to different things. And how to do that on the Siemens PLC, I haven't got the slides I did. Like I said, I'm learning that. So I put that IO module on there. I have no idea how to address it. I'll find out. Ladder logic program, 7% system memory, executed information, 20% of the memory. These are the different files. So we just saw those, right? So we got the ladder logic. That's all in what they call ladder 2. Now why they don't use ladder 0 and ladder 1 in Allen Bradley, I don't know. So your base program is going to be in ladder 2. Then we have the input status. We looked at that in the PLC, the output status, timers, counters, and then we got all this other stuff, all your math and logic, which would deal with your integers and that kind of stuff. So all your memory is divided up inside the PLC. Of course, what they're doing is they're actually giving you addresses. What they? Network communication. We talked about this a little bit. These are the 3 methods we can go with an Allen Bradley PLC. They call it the Data Highway 485, which is for years we had the Electronic Industry Association, EIA. They established a lot of the hardware that deals with computers. About in 2009, they disbanded because there was other people out there that could do that. But all the interfaces went over to the internet, TIA, Telecommunications International Association. So we used to have what we call RS-232, which was that serial interface that we looked at. RS was recommended standard. So all of the EIA standards came out with RS-232. Probably as you get in with people that's been in the deal for a long time, they're going to call it RS-232. They're going to call this RS-488. They're going to say RS-422 because they're still on the old standard. Odds are you can probably still look them up on the internet, but probably in there somewhere they'll say, well, this standard is now managed by TIA. Or sometimes they say IEEE, which is the International Electronic Association. These are basically just serial. What do we mean by serial? Yeah, one bit at a time. We're sending bits. We got 2 ways we can send bits. We can send them what we call parallel, or we can send them serial. Parallel is always a lot faster, but it's very expensive. So this would be like me making a 16-lane interstate going up to Birmingham. It'd be very, very expensive. It'd be very, very fast. Right? I could build a 1-lane road up there, and eventually everybody would get there, and everybody would get home. But if it's just a 1-lane road, you would have to take turns, right? So 2-lane roads would be the route we would go. So we could not only stand and come back, and everybody would get up there on a 2-lane road, right? It would just take a lot longer, but it'd be a lot more expensive. And then we've got hardware, we got relays, we got all this other stuff. So a lot of times parallel just don't make sense. So if your hardware is not as fast, so used to the hard drive interface that we used to send information back and forth between our big disk drives were parallel interface. We used to call it parallel ATA. They came out with something called serial ATA, which is serial. What they did to get the extremely high speeds is they used a different electrical technology, which made us go extremely high speeds, but we could do it serial. Now they could implement that same thing on parallel, but there was no need because there was really nothing out there that needed it anymore. So serial ATA, Ethernet is serial. Ethernet is serial. That's why we only got 2 wires. We got 2 wires to transmit and 2 wires to receive. It's a USB. What does the S stand for? Serial, universal serial bus. It's serial. Ethernet serial. Wi-Fi is serial. So when we're sending these packets out there, by the way, in here, if you're on your wireless network, if you're on this access point, how many computers can be accessing that network at any one time? 1. But they do it in a packet. They send out a packet, then what do? They release the network. So Ethernet is what we call carrier sense multiple access with collision detection. That's what Ethernet is. Now, the internet uses something called baseband. But as soon as you go to baseband, we got to start adding these things called modems because all that information is modulated. So what they do is they modulate it on a carrier, and then you can have multiple things riding on different sections of the carrier at the same time. But what you end up with is you end up with all your equipment now is going to have to be extremely expensive, right? So local Ethernet right here is all carrier access, carrier sense multiple access, and collision detection. So all of these are serial interfaces. It's just that Ethernet. Alan Bradley calls theirs Ethernet/IP. That's what they call it. But it uses, what's nice about using Ethernet is all your devices still work. So I could send this stuff over this college network. So I can send it through Wi-Fi. I can send it through wired. So, by the way, wired Ethernet is a heck of a lot faster than, they brag about 100 megabits. On wired Ethernet, we're up in the gigabit. So wired is always faster than through the air, right? So these are 2 standards. Data highway is actually an RS-488. And this is, I think it's an RS-422. And this uses the same cable that I've got. But we can use switches, we can use routers, we can use all the stuff that's already out there. Now normally if you're going to put it out in the shop, you're going to use industry grade stuff. So you'd use a special switch and a special router or something like that. SEMA, and they left one out completely. We have another one called DeviceNet, which is supported by Siemens. By Allen Bradley PLC. So DeviceNet is where it is. DeviceNet is set up to control anything besides PLCs. So we can buy valves that are DeviceNet. So we can actually, instead of me running a wire out to the valve, we can hook that valve up to the network. So I can energize the valve or de-energize the valve through a command So what you do is you'll sign an address out there. DeviceNet, when you do it, you have to go out there and actually flip things to sign in a DeviceNet. But with DeviceNet, we get an address up to 200, it's either 128 or 256 devices out there on a DeviceNet network. If you ever went out and looked at the big Bannock robot, I think they've got 8 channels up there. Well, each of those 8 channels could control 128 or 256 guys. I'm sorry, it's one of those numbers, different things. But every one of them's got to have a unique address, right? You understand? So what you do is all these devices have these little switches on the side. You just flip the switches to assign them an address. So, but now we can have devices besides PLCs communicating with each other. We can communicate with relays, we can communicate with valves, we can communicate with other PLCs. So that's the network program. I don't know if we got any Ethernet available control valves and stuff like that. I'll check on that too. Siemens usually has 2. They use Profibus or what they call Profinet. The way you connect things together to communicate. But these are all available. These are your older protocols. These are the ones that we still use. Most of your big mechanical devices that you control, if you're using Allen Bradley, you're going to use devices. Connect the PLCs together. You're probably now either going to use DeviceNet or Ethernet. Does that make sense? So if you use DeviceNet, you got all these different controllers and all these different types of things. It's really neat. We try to talk a little bit about it in industrial robotics. If you take that class, how we can connect these robots together. They don't call it DFI. Provide serial communication through RS-232 interface. That makes sense now? Yes? No? RS-232, we got 2 options. Originally we used what we call a DB9. Let's go right here. This is RS-232. They didn't define the connector. Well, they did define the connector, but RS-232 defines the wires in the cable. Which ones transmit, which ones receive, which one's this, which one's that. And that's defined by the RS-232 interface, which now we call the TIA 232. And then what they did is eventually, so originally when we used to hook up our mice to a computer. Now how do we hook up a mouse to a computer? Bluetooth or USB? Okay. But originally when they came out with the IBM PC, originally RS-232 was a 25-pin connector. And then IBM said, we don't have enough room. So IBM dropped it down to a 9-pin connector because they didn't need all those different cables going through there that the original RS-232 defined. So they dropped it down to a 9-pin cable, and that became our mouse. That was our mouse. So we'd have to run that thing and plug it into the back of our computers. So some of our old computers down there that's running the old Celeron processors, the PLC is going to plug into these. Now what happened over time is that they wanted to keep wanting to decrease the size of their computer. So eventually what IBM did, and IBM set a lot of standards, is they dropped the RS-235 down to this connector right here. So this is also RS-232. A little round connector. So a lot of the keyboards you look, you'll see the mouse plug in with one of these. The problem they did is they assigned the mouse and the keyboard the exact same connector. So what did people do all the time? Yeah. So they set up a color code where purple is the keyboard and green is the mouse. So now when you go out and buy one, this will be green on the inside, and that way you know which one to plug it into. It didn't hurt anything. If you plugged them in backwards, your keyboard or your mouse didn't work, but it wouldn't hurt anything because it was still the RS-232. So just about all of your Allen Bradleys that's still supporting the the data highway has gone to this guy right here for their RS-232. But you can see it's real easy now. We just plug it in to the side. And also we got the Ethernet connector over here, the RJ45 connector, which is that 8-pin connector right here. This basically looks like your telephone connector, but that's what we call an RJ11. An RJ45 actually has the 8 pins on it. So that's an RJ45 connector. So a lot of your PLCs now are going to Ethernet. Now the problem we have is that this guy considers itself to be a computer. This guy considers itself to be a computer. So if I was to plug this into a switch, we have no problem. So we use what we call a straight through cable. If I'm going to take, we call this a data terminal equipment, and all your other things we call data communication equipment. Well, if I take a DTE and convert it into a DCE, then I use a straight through cable. But both these guys consider themselves to be a DTE. So that means what I'm transmitting over here would go to the transmit here, and what I'm receiving over here would go to the receiver here. So what we have to do, if we're going directly there, we have to use what we call a crossover cable. And so what I'm going to do is I'm going to swap this around, and you'll look at one of them. You look at the color codes, and it's orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. And then I come up and look at this one. This is green, white, green, right? Then it goes brown, white, blue, right? And so what they've done is they've rolled the transmit and receive. So this is what we call a crossover cable. So normally if you're going to connect directly to, if you're going to connect to the PLC through a network, then you use a straight through cable. If you're going to connect that PLC if you're going to connect your computer up to the PLC, then you have to use what we call a crossover cable. So, you understand that? So this is a crossover cable, because I'm connecting that directly into this PLC. But if I was to take this and hook it up to a switch, then I would use what we call a straight through cable. If you take the cable splicing and installation course, I'm pushing all my courses on. We teach you how to make those. Teach you the color code. It's not real hard. We call it a 568A and a 568B. If you're going to make a straight through cable, then you use the 568B on both sides. If you're going to make if you're going to use a crossover cable, you wire one of them to the 568B standard, and you wire the other one to the 568A standard. And y'all can look those up. Provides serial communication through RS-230 interface. So what we have on this guy is we've got two methods we can hook up the data highway. We can hook it up through coax cable. So y'all would probably have to come up here. In fact, let me take off the door and I'll pass it around. So we got two methods we can hook this up. We can hook it up through the data highway, and I didn't bring my camera out. So let me switch over to my, and then I'll pass this around and look at it. Is that me? I'm frozen time. Okay, there we go. So this one right here is the way we would use coax. So it's a 2-wire coax with a shield. This is the RS-232 connector right here. So this is the other way we would hook up the data highway. And this is if you hook up a dedicated terminal. So we won't be using this. By the way, here's the number for the CPU. It's right down at the very bottom. We're using this method right here. We're using the RS-232. Okay, and that's what y'all will be using down there. Except on the 1000s, instead of having a DB9 to a DB9, you'll have a DB9 to that round connector. Have I lost anybody? DFI is not used anymore. That didn't have then we have RS, we have the next one. Did they talk about that? 2 types, full duplex and half duplex. Full duplex. This is what your cell phone is. So we have simplex. Simplex is communication in one direction. So TV stations use simplex. So they send you that thing and you can't communicate back to them, right? That's simplex. So simplex is communication in one direction. Then we have what we call half duplex. This would be like communicating on ham radio or the LCD radios or 2-meter radios where only two people can speak, but they can't speak at once at the same time. So that's, you learn. Yeah, that's half duplex. 2 directions, but not at the same time. So you're still doing it on 2 wires, but you're not doing it at the same time. They called it Mars. When we was in the service and we was in over Japan, that's before we had cell phones and all this other kind of garbage. And all we had was dial-up phones. Well, to call from Japan to the United States would cost you a ton of money. So what they did is they had these ham radio operators set up all over the world that would handle that. And what you'd do is you'd call into them, and then they would send it over the ham radio. And so you had to learn to say over and all that other kind of stuff. We walked in on a guy who was talking to his wife, and he said, "I love you, over." We got tickled. I'll never forget that. I love you, over. Full duplex. This is what your cell phones use. This is what Ethernet uses. So full duplex means what? 2 directions at the same time. But if we're doing it hardware, we got to dedicate at least 4 wires. DF1, I have no idea. That's a perfectly legal question. It's a form that Alan Bradley originally used to network the PLCs. Now DH stands for data highway. But if you find it, let me know. I'll be happy to say it for you. Everybody okay? By the way, so how am I going to remember all this stuff? Well, listen to the book. And then also what I've done to keep you, didn't I show you all this? There's a glossary up there. There's a glossary up there inside course content, inside reference materials called a glossary. And every bit of these terms are in there. Not only does it need telling you what it is, you can actually, it'll tell you about DFI, and it'll tell you about, I don't know what it stands for. It's up there. Full duplex, half duplex, serial communication. We've already talked about this. What's the advantage of serial communication over parallel communication? Got one advantage.
Powerful one. Is that right?
I'm not good at that. Cheaper. So that's why your networks are serial. I mean, if I looked up parallel, 32-bit parallel, that means I'd have to have 1 wire running through this campus to every computer, right? But if you do it serial, then we're sending it 1 bit at a time, right behind each other. And now we can do what? We can send, it's a lot cheaper. Yeah. So parallel, everything inside the computer is parallel. But odds are, when it leaves that computer, it's going to be serial. With our new interfaces, serial ATA, guys, that is amazing. It uses something called differential interface, and I'm not going to get into it. A differential interface is basically immune to electromagnetic interference. We can use extremely low voltage levels. We can do it extremely fast. So right now, there's probably hardly any hardware device out there that could keep up with serial ATA. I could do it parallel. There's a SCSI standard that uses differential. SCSI to communicate with some hard drives. But these guys, SCSI, small computer system interface. These guys are pretty big mass hard drives that we don't even understand.
We say, okay, I got a 2 terabyte drive, you know, these big servers, these guys got drives you just don't believe. And odds are they're extremely fast, and so they're probably using different stuff on those things. But we don't need it, right? You understand? So we're using serials, USBs, uses differential signaling, Ethernet uses differential signaling. We're already up to a gigabit per second on wired Ethernet. So there's really no need to use parallel. It's just so much cheaper, right? You understand? So all these buses, all these communication networks that we're talking about, these were all serial. I don't know any parallel networks.
Even the internet is serial.
So what's the advantage of serial? T-Bar, what's the advantage of parallel? Fast, but very what? Expensive. Yeah, it don't make any sense. It don't make any sense for me to have an interface that's faster than what I'm using. That when they came out with a F4 Phantom, that thing run 2 big old I forgot what engines they were. Those engines could push that plane faster than that plane, than the airframe could handle. So they never ever run those engines wide open. The airframe couldn't handle it. So it was a waste of money, right? But that thing was big. I don't know if you ever saw the F4. Yeah, Pratt & Whitney, but I don't know which one it was. We ran Pratt & Whitney in J45s or something like that in our phone. But we were turboprop. So I've got these memory devices out there. I've got these hard drives. I've got these solid state drives. And serial ATA is faster than what those things are anyway. So it'd be stupid to do what? Spend all that money. Now inside the processor, where your processor running at 2 or 3 gigabits per second, serial would just waste time, right? You understand? So inside the computer, all those buses, all those address buses and data buses, those are all parallel. I love you, Over. Compared to parallel and serial, parallel each bit has its own fast and very expensive. Serial is slow but inexpensive. Now, when we say slow, we don't mean it's slow. We mean it's slow relative to one. Parallel. It's fast. Fast enough. So this would be parallel. Oh, that's out of my book. Somebody didn't give me credit for it. I'm probably the one that put it in there. And this would be serial. And it's real neat. USB is really neat. How these packets are put together, what they contain, how they go out, how does the receiver synchronize with this, how does it know what the ones and zeros, there's a lot more to it. Luckily we don't have to know that. And we're not going to spend much time on parity. We don't use that much anymore. And DTE, good gracious, all this is in there. DTE, data terminal equipment, what are these? These are guys that initiate and terminate communication. So what would a printer be? It'd be a DTE. What would a computer be? DTE. Anything that controls it or it passes through, these are what we call DCE, data communication. So in Ethernet, your routers, your switches, your gateways, all these would be considered to be DCEs. And this is where you got to know the difference when you make these cables. So if you hook a DTE to a DCE, you hook a straight through cable. If you hook up a DTE to a DTE, then you got to use the crossover. And we don't hook. We do hook DCEs to DCEs, but it's while that travels through, right? You understand? Because they don't initiate the communication. All they do is repeat it or route it or switch it, right? You understand that? But they don't initiate the communication. So we communicate with DTE, but we communicate through DCE. Does that make sense? Yes? No? Have I lost them? Are y'all, after lunch, are y'all going to sleep on me? Simplex, half duplex, full duplex. So
You'll notice we have to add, if we're doing this electrically, we have to add 2 different wires. What they do on Wi-Fi is they use 2 different frequencies. They use one frequency for transmit and one frequency for receive. So that simulates one carrier frequency.
What's the example of simplex?
Simplex is TV stations, radio stations are simplex. What's that? If I'm sitting out there in my car, I'm listening to that radio station, I can talk to that radio all day long. You don't go anywhere. Because simplex is communication in one direction. So printers used to be simplex. They're not anymore because they communicate all this stuff back to you. But originally, printers were simplex. We just sent them what we wanted to print, and then that was it. But now our printer tells us when we're out of ink and when we're getting low, so that has to be what? That's got to be some type of duplex. You can't scream at it. But the other people over there don't hear it.
So we got different ways we can connect networks. We have what we call a bus topology, which is not in here. Is that in your book? A topology is the way we connect the network together, physically connected together. We call that a topology. So DeviceNet is a bus topology. So what we do on a bus topology is we have one conductor. They usually call it a trunk, and it runs the entire length of the network. And then we have to put terminators on it so we load the cable correctly. And then what we do is we tap off to it like this. And this would be what we call a bus. Then we have what they call a daisy chain bus, which is so here you literally have a cable and you come in, and what we used to do is you used to put these T's, and this is what DeviceNet is. So DeviceNet is a bus. So anytime I want to tap off to my trunk, I would have to insert this thing called a T, and then it would tap off like that. And it's all screwed in. I might, if I can remember, I'll bring some DeviceNet stuff over here for you. But what was happening was that if we didn't terminate it, then this communication would come back down here, and it would be very, very noisy. So we had to put these terminators out there. Then we have what we call, it's still a bus topology, but they call it a daisy chain bus, where we bring it in, and these are my PLCs, and the cable would come in, and then it would piggyback on the other one, and then it would bounce down and piggyback on the other one and bounce down. And this is why it's called daisy chain. So it's not, we don't have a cable that runs down here. And then what you have inside your connector is you have a little switch. So the last one on the line, you'd flip in that terminator. And if you wanted to add another one, you'd just flip it off on this one, then you jump another cable and then switch the terminator in. This is called a bus topology, but we call it a daisy chain. A daisy chain is just jumping from one to the other to the other. Then Ethernet uses, Ethernet was originally a bus topology, and that's why I said we got all this coax cable running up through the ceiling through here. I think there's still a drop in this office back here. It's got a coax cable. That was 10 base T. I mean 10 base T is twisted pair, but it was 10 megabits. Then they came out with a star topology, which is what we normally use now. Star, yeah. And what we do is we have a central device called a hub or a switch or a router. And then we come up here and we put these, and this is why I got this name, the star. Of course, these, and then, so everybody's got their own cable that runs back to the central unit. And this would be called a star. And you could bring this out and then hook this up to another switch or something, and you could come out and do that kind of stuff right there. Or you could have a switch or a router or whatever. And this is called a star topology. So this Ethernet IP, Profinet, this is a star topology. So you'd have to have a smart device. Originally we called it a hub. Topology. So what is the topology? The topology is the way we connect the network together. A star has multiple. I don't know what you mean by that here. Originally, we used something called a hub.
Can you just keep going and going?
Well, over as long as you stay within the address range. These cables, if this is a wired cable, the maximum length is 100 meters. Before you go through a repeater or anything like that. 100 meters, about 330 feet, which is a pretty good distance. It don't mean you couldn't run it. The ORS-232 interface was supposedly good for 50 feet. And that was, they don't guarantee it after that. I saw some RS-230 things running thousands of feet, and they still worked okay. But the specification for Ethernet is 100 meters between electronic repeaters. And this is where glass fiber has, in glass fiber, we're talking about thousands of kilometers. So originally, we used something called a hub to connect it together, and all it was a repeater. So what was happening was this guy right here would come out. If he wanted to put data, it would go out to everybody. It would go out everywhere. It would go out the whole network. And so that meant only one device could be on the whole network at any one time. So then we came up with something called a switch. So that's what we use now. You don't hardly ever see any hubs. You see a switch. Now what the switch does, it learns the MAC address of every device on the network. And it learns the IP address of every device on the network. So if I was to come over here and I will say I want to communicate with so-and-so, so let's just call this computer A, and I don't have the rest of them, B, C, D, E. So E has a packet for computer A. Well, you'd have to know the IP or the name. And then what had happened is it would come into this switch, and the switch knows where A's at. And it would connect to A, and nobody else would get traffic. So that means C could connect to B, D connect to E. The only time you would happen if another computer came up here and wanted to connect to A, then A would have to work. So just going to switches increase the speed of Ethernet, in magnitudes. Then we have what we call a router. A router allows you to divide it up into what we call subnets. So when you set up an IP, 192.168.80.32, there's a portion of this which we call the network ID, and then there's a portion of this we call the node ID. And then what you do is you establish what we call a subnet mask that tells your routers and everything what's the network ID and what's the computer on that network ID. And then what you do is when it sees like 192, so 80, 80 might be one route, and then the other route might be what? Like a 66. So what would happen is, as long as I used one that had 192.168.80, then this switch would keep it in here, right? You understand? If it came up and I used the 192.168.66, and it says, oh, that's on a different network, and it would broadcast that to the next switch or whatever down the line. So what was nice about routing, it allows us to split our network up into subnets. Thank God, because that's what the internet is, right? You just got thousands of subnets, and when you specify that IP address, of course nobody knows IP addresses. Y'all know IP address?
How do they handle that? Originally, this is what we had to do. You still have to know this if you want to get onto what they call the dark web. So they steal IP addresses. But what you do is that we set up what we call a DNS server, which is a domain naming system server. And when every one of your IP, every one of your names ends with like a .com, a .edu, a .gov, a .org, yeah. So what we got is we got these guys called DNS servers out there, and they're nothing but phone books. And if you say .org, it goes to a computer that's got everybody's IP that's got a .org domain is listed on it. And then what they do is they take your IP address and match it to, they take your name and match it to a what? An IP address. And then they send that on down the line. And they keep up with where that came from, right? And then all that's in your TCP/IP packet is the destination computer IP and the originating computer IP. So DNS servers. So we got DHCP servers. What do? Well, they automatically assign IP address for us. DNS servers are phone books. It allows us to use a what? Name instead of number. So in my phone, I got what they call a contact list. That's a DNS server. So instead of me having to know my son's, and this happened to me, a guy called one of my son's number. I said, I don't know. I didn't have my phone with me because that's my DNS server, right? You understand? So I go in and select a what? A name, and then what? Then it gets the number. Well, that's what a DNS server does. So what we do is we specify a .org, a .com, a .edu, and then we got different ones. We can specify a country. So we can put I think it's .en for England, and then we can start repeating IPs over there. We got BUS, which almost nobody uses, which is business. They added those domain servers out there. So now y'all know how the internet works.
If the test gonna be Tuesday, Thursday.
That's gonna be cheap. Gotta do it. We only got 8 weeks, got 3 tests to do. So I'll give y'all a review sheet. I'll put that online.
Okay, I was gonna do that next week.
Put that out there. If you got any questions on the review sheet.
What about the labs? Are we physically going?
Well, the problem we have with labs right now is some of y'all don't have their lab. And what they had to do is they had to reorder them. So that's basically what we're waiting on to get in the lab. And that, unless I can start making copies of it, that's what I'm gonna do. I'm gonna start making copies into the lab box. But legally, about the only copies I can make out of a copyrighted book is 3. And then once I do that, then if it got out, then I could do.
Everybody make 3 copies.
Yeah, but that's up to you. I'm not telling y'all to do that, but if you borrow somebody's books and make copies. Are you okay? Huh? I'll do it. So there's a section on Blackboard called Test Reviews. And for your terms, you're going to go and look at what? Glossary.
Where do you want these parts?
I want to back over there. They're
Leave them
teaching.
here?
No, I want to back over this table.
Okay.
They're teaching a AC class, and I think.
Yeah, 6.
This one you said over here?
Teaching hydraulics and pneumatics as well.
Okay.
This many turn on or you're on. Is there a summer cut?
I do have some more. I'm gonna make pictures here.
I don't know.
If I want.
I can show you what we're gonna teach at some during the day. I don't have the night schedule.
And what, I mean, the main thing I would think, so you go over controls of hydraulics and pneumatics mostly, or and also pressures and stuff.
Yeah, how to calculate pressure, force, speed.
Because my AOT is in building and industrial maintenance.
We have quite a few, oh,
So also, but I've signed up for more classes, all my classes now are